Hello there, fellas, and welcome to another video. Alright, so today I'll be deriving the centripetal force equation. It's an equation you may have seen in high school or college physics. Specifically, it's the equation that tells you the force that must be exerted on a particle, assuming that it follows a circular path and with a constant velocity, and the mass of the particle is also constant. It states that the magnitude of this force, which is what we call the centripetal force, is equal to mv squared over r, where m is the mass, v is the velocity, and r is the radius of the circular path. Additionally, the direction of this vector must point toward the center of the circle, so that's from the particle and to the center of the circle. But, why? Why is this true? Well, in this video, I will be answering this question. To begin, let us construct a circular path of radius r, and in the xy plane, of course, and we'll have a position vector, r of t, as displayed there in green, and then we'll also have a mass that the position vector points toward in blue, and we'll illustrate this mass as a sphere. This is a particle mass, so it acts as one absolute unit, and the mass of this object is m. So our mass will travel in a circular trajectory at all times, and so the goal is to find the magnitude and direction of the centripetal force vector, which is the vector that keeps the mass on this circular path at all times. Alright, so here's an overview of how this problem may be solved. So we start with force must be equal to mass times acceleration, of course, and the mass is given as a constant called m, and the acceleration, however, is not explicitly given, but we know it's equal to the derivative of velocity with respect to time. And we also know that the velocity is the derivative of position with respect to time. And we also know that position, in this case, is a circle with radius r. And the circle will be centered at the origin. However, it could be centered anywhere, but for simplicity, it will be centered at the origin. Also, the magnitude of the velocity vector must be equal to a constant, and we will call this constant v naught. So we could use this information to solve for the centripetal force Fc of t, and then we could do an extraction procedure where we extract the magnitude and direction from this vector. It is a very careful procedure. It must be done with utmost caution, I advise you. Alright, so now we can express the circular path that is centered at the origin with radius r as the square root of x squared plus y squared is equal to r. Then, also, we can parameterize this equation by theta. We could say that x is equal to r cosine of theta, and y is equal to r sine of theta. And we could say that our position vector is equal to r, as we see right there. However, there's a problem. There's a problem. Theta must be a function of t, because r is a function of t, right? So that's the logic. So we have r as a function of theta. However, r must be a function of t, so therefore theta must be a function of t. So we'll make that change in the next slide. And as I had promised, we indeed did make this change, as highlighted in red right there. Alright, so we have found r of theta of t, and we can combine it with the fact that the derivative of r of theta of t with respect to t must be equal to the derivative of r of t with respect to theta multiplied by theta, the derivative of theta with respect to t, according to the chain rule. And now we could combine this information to get the derivative of your path with respect to time. And so we know that this derivative of the path with respect to time is exactly equal to the velocity of your particle. And so if we combine this information, then we get the expression for velocity as a function of theta of t. Yeah, which could simplify to that. But hey, what is theta of t? Or sorry, what is the derivative of theta of t with respect to t? Because we don't know theta of t. So how do we solve it? All right, so we begin with the velocity in terms of theta of t. But we also know that the velocity, the magnitude of this velocity, must be a constant equal to v naught as our constant. So if we combine this information, we get the magnitude of that one expression is equal to v naught. And using this, we can actually solve for d theta by dt, which is exactly what we need. All right, so now we will retain the information in green about the velocity, and we will further process the equation in blue. Let us further process this equation by expanding the magnitude. And then we recognize we have a sine squared of theta plus cosine squared of theta, and this must be equal to 1, using that one trig identity. And now we may proceed with the simplification and finally solve for d theta by dt. We say that d theta by dt is equal to v naught over r. So we retain the information in green about the velocity, and we retain the information in blue about the derivative of theta with respect to t, and then we could we could substitute v naught over r for d theta by dt, then we can make the following conclusion: that velocity is equal to v naught multiplied by the vector negative sine of theta of t comma cosine of theta of t. And so now we have found v of t. Specifically, we have found v in terms of theta of t, which is exactly what we need for the next step. All right, so now we retain this information that we have about v of t, and now we combine it with the this one equation that is a result of the chain rule, which says that the time derivative of the velocity is equal to that stuff right there. And then we could sub in v naught over r for d theta by dt in that chain rule equation, and then we could proceed to combine this information. We obtain this, and we know that dv by dt is actually equal to the acceleration. So we make the following conclusion, that the acceleration is equal to negative v naught squared over r times that's one vector that is a circle, the unit circle, actually. And so we have found a of t, specifically a of theta of t, which is exactly what we need for the next step. So now we could solve for the centripetal force. So we combine the information with Fc of t is equal to mass times acceleration, and we obtain the centripetal force equation right there. It is found. It was lost. And now we have found it. And now we will proceed to the most delicate part of this operation, the extraction procedure. So if we extract the magnitude from this vector, successfully that is, then we obtain mv naught squared over r, which sounds very familiar to me. Then if we do the direction, we extract the direction by taking the unit vector in the direction of FC of t. Then we get negative cosine of theta of t, comma sine of theta of t. And notice that this is the, so without the negative sign, this would describe all points on a circle. So it'll point towards some point on a circle, according to theta of t. But since we add in the negative sign, we have reversed the direction, and thus it will point toward the center of the circle instead. And here's a summary of our findings. We found that if an object of mass m travels around a circular path of radius r with constant velocity v0, then the centripetal force vector, Fc of t, has magnitude mv squared over r, as shown right there, and it points toward the center of the circular path, as shown right there. And so another thing that I want to say is that remember this information over here, we have d theta by dt is equal to v0 over r. So guess what? We could solve for theta of t if we really wanted to, but that wasn't really the goal. We only need to say that it points toward the center of the circle. But if we wanted to find the direction as a function of time, then we could combine that d theta by dt information with the upper and lower bounds of theta. And there you go. And also, that points toward the center of the circle right there. Alright, so that's it. Thanks for watching, and have a great day. Or if it is nighttime, I hope that you awaken fully rejuvenated. And also, make sure you subscribe. That'll be pretty nice, because if I get 500 subscribers, then I will be able to sell stuff, which will be pretty cool. You'll get some nice, cool Pioneering Proofs merchandise, like a t-shirt, or a mug, or a bandana. That'll be pretty cool, right? Yeah, so see you later.